Yeah, good morning, everyone. I'm going to talk about two parts in this lecture. First of all, the lecture A is going to be about GenASM, and the second part of the lecture is going to be about a recent project of ours, Scrooge, which builds on top of GenASM, is pretty closely related. So yeah, welcome to lecture 8 of our PNS Genomics course. All right, let's start with a high-level overview of GenASM. So genome sequencing, as you know, if you're watching this course, plays a pivotal role in an entire range of applications such as personalized medicine, outbreak tracing, and the understanding of evolution. Now, the modern sequencing machines extract only small randomized fragments of DNA, which are called reads. And the key pointer is that these reads have very different properties depending on the sequencing technology used. So this can be short reads, which are a few hundred base pairs, or long reads, which can go from thousands to millions of base pairs. That's also relevant to the alignment algorithms, which Scrooge and GenASM are, is the error rate in these reads, which also varies a lot. Okay, there we go. So how we analyze these short reads is with read mapping, where we align the reads to possible locations in the reference genome. And the goal there is to find basically where a read matches in a known reference genome and how, if it differs, how it differs from the reference genome. And in multiple of these steps, there's a step called approximate string matching that's required as part of read mapping. And we need the result of approximate string matching later in downstream analysis steps to really make useful decisions based on the reads. Now we observe that these are typically bottlenecked by both computational power and memory bandwidth. So both the works that we're looking at will try to be as efficient as possible in terms of computational bandwidth. So in GenASM, the goal was to accelerate approximate string matching by having a fast framework, of course, and it should be flexible in terms of supporting many types of reads, for example, both these short and long reads. And it should be also usable for multiple steps of genomic analysis. So I'll focus on the read mapping, but GenASM can be used for for example, pre-alignment filtering as well. So in this work, they proposed a GenASM, which is based on the BiTAP algorithm. And it's very interesting because it uses only bitwise operations. And then they had to extend and modify that algorithm a lot, such that it scales to long reads, such that we get all the output of it that we need. That means they include traceback, and it also includes a hardware algorithm co-design. So while they took this algorithm that was already interesting, they tuned it such that it's very suitable for a hardware implementation, and then made that very efficient hardware implementation work. And that ends up in a very low power and very area efficient hardware accelerator. Okay, so this GenASM thing, as I said, it should be flexible and should be usable for multiple use cases, and that's what ended up happening. So the proposed use cases here are read alignment, pre-alignment filtering, and edit distance calculation. And you can see significant speed ups over prior works in all three cases. Okay, so that was supposed to be a short high-level introduction. Now we can go into a bit more detailed background and take it step by step from there. So again, this read mapping pipeline that we need for genomic analysis, it's really central to many end-to-end analysis. So we start with sequencing, we get out raw data. Let me enable a laser pointer here. We start with sequencing, we get out raw data. Then we send this raw data to read mapping to compare the raw data to a reference genome. Then we do variant calling to get a consensus between many noisy reads to get a really high confidence output. And then finally, the scientific discovery part builds on top of all these steps. And it turns out read mapping is typically the bottleneck here. So as you can see, for example, the Illumina high-sec machine has really, really high throughput of 300 million bases per minute, but we cannot map that quickly. So the computational step is what slows everything down. If your result is scientific discovery, we really don't want to slow down a scientific discovery by 150x because we're computing too slowly. So that's why this is important. So we should look at the read mapping pipeline in detail. Now, the read mapping pipeline consists of 4 major steps: indexing, seeding, pre-alignment, filtering, and read alignment. So the indexing step indexes a reference genome. It builds essentially a hash table-based index from the ACGT sequences in the reference genome. This is kind of a reverse lookup table of locations. So we can find small strings that match exactly very efficiently using the hash table. And then in the seeding step, we obtain a read from the sequencing machine, and we can check in the hash table where it might fit well. Now, this results in a huge number of mapping locations, and to efficiently evaluate those, we want to quickly reject many of them. So we will get many potential candidate locations of a read in the reference genome, and the pre-alignment filtering step should quickly determine that most of them don't fit well and reject them. Okay, we need a reference segment and a query read from there, which can be obtained by just looking up parts of the reference and read based on the seeding. And then finally, the ones that pass the filter, they go into pairwise sequence alignment or read alignment. And that optimal alignment is then the final output of read mapping. So as it turns out, this realignment part is really very much of the issue is in this pipeline. So if you look at this recent paper, so accelerating long read analysis on modern CPUs, they benchmarked this state-of-the-art read mapper, Minimap2, and they observed that in many of these cases, not all of them, but in many of these cases, the read alignment is really the bottleneck. So you can see here on the y-axis execution time, and just the vast majority of the execution time is occupied by the gray bar, which is alignment. Okay, so what's pairwise sequence alignment? Just let me briefly repeat that, although we've introduced it in the course before. And we want to compare a pair of strings while allowing substitutions, insertions, and deletions. So a substitution means given 2 strings, some characters will just be different. So you will still have the same number of characters, but individual ones will be replaced by a different one. And then we have insertions. So here you have different length strings, where there's one character missing in one of the strings, and it's there in the other. And then we can have deletions, which is the same as an insertion, but it's the other string that's missing the character. Okay, now we want to find a set of such edits, we call them substitutions, insertions, and deletions, that are minimal. So we want to have a minimal set of edits that determine all the differences between these 2 strings. And we report afterwards all of these differences using a string like this. So we're saying, okay, 2 characters are equal. One character X means one character is mismatched. Then another character is equal, another character is mismatched, and so on. For the insertions, we do a similar thing. We just say it's an I instead of an X. So 2 characters exactly equal, 1 inserted, and then another 4 characters exactly equal. Similar thing for deletions. This representation, that's really the key output of pairwise sequence alignment. This is called the cigar string. This is really important because this was later needed by variant calling. So we really need this as an output. So how we classically calculate this is by arithmetic dynamic programming. We've introduced this before in the course, I believe in some overview lectures. There it was called just arithmetic, that it was just called dynamic programming. I'm saying arithmetic dynamic programming here to contrast it with GenASM. So recall that this dynamic programming works with numbers. So we initialize a top row on the leftmost column with numbers, and then based on 3 entries, we calculate one new entry using arithmetic operations. So this algorithm is called Needleman-Wunsch, and there's it was, I guess, invented in many places at the same time, and then there's extensions on top of it, which were developed over the years, such as Smith-Water and Goto, and recently WFA, which looks quite different, but it's still arithmetic based. So yeah, most of these algorithms work over tables of numbers. Of course, by the way, we apply the same rule, this update rule of 3 neighbors to all entries, and not just the first one I highlighted here. Okay, now this was arithmetic dynamic programming. What's interesting here is this BiTAP algorithm. That's the algorithm that GenASM builds on top of. This BiTAP algorithm uses bit vectors. So if you compare that to this Needleman-Wunsch table down here, which contains numbers in each entry, the dynamic programming table contains bit vectors. So this is 0s and 1s. And as you can see, also the layout is quite different. So you have one axis which also contains ACGT at the border, like down here, but the y-axis is actually not ACGT, but edits. Basically the so this is the text in the Needleman-Wunsch and BiTAP case, and the y-axis in the Needleman-Wunsch case, let's call it pattern, is kind of laid out also on the x-axis, but within each bit vector. So you can see there are 4 letters over here. That's why each of these bit vectors is horizontally 4 bits. Okay, and then the y-axis is number of edits because, well, we somehow need to represent the dimension that the numbers here capture. Now, this BiTAP algorithm is particularly interesting because although it still needs to take 3 neighbors to compute one new entry in the table, it can do so using only bitwise operations. Of course, you have bit vectors, you use bitwise operations. And it's really interesting to use bitwise operations because these can be particularly efficient in hardware. So hardware kind of, if you have to design any kind of hardware, you typically start from XOR gates, or NOR gates, something like that. Anyway, the point is you start from binary logic gates and you combine them for more complex logic functions, such as maybe an arithmetic logic unit that you need to execute this algorithm over here. It's much nicer because if you just actually need to execute bitwise ANDs and bitwise ORs, that's really what the lowest level of your logic can do very efficiently. Okay, so this is how this table looks visually. Let's briefly look at some pseudocode of this algorithm. So this BiTAP algorithm, yeah, as I promised, is use only bitwise operations. So some bit shifts here. This is a bitwise OR, and then there's some bitwise ANDs in here, but it has some drawbacks. So it has a large number of iterations. As you can see, it's an outer loop and an inner loop. So it's a square table, of course. And okay, that means it grows quite quickly as sequences get longer. For example, for long reads, we will start to struggle. And then there's data dependencies going on. So we have in the inner loop data dependencies. We have so we have basically data dependencies on the previous outer loop iteration. Sorry. So this old R that's referenced is the R from the previous iteration. So we cannot parallelize multiple of these iterations essentially. And the inner loop also has dependencies because we are accessing RD-1, which got written to in the previous iteration. So also in this direction, we cannot just easily parallelize the inner loop. Typically, to execute any of these algorithms fast, you really want to have a parallel version of it to use SIMD or something similar like that. Then BiTAP has another issue. It's not just lacking this kind of parallelization, it's a bit slow, but it also lacks some functionality that we need. So recall that we really want to report these cigar strings, this list of edits to convert one string into the other. And for that, we need something called traceback. And BiTAP out of the box does not support it. It supports calculating edit distance, but it cannot support calculating how it got to that edit distance. So what that cigar string is, and we need that. So again, let me reiterate. So there's data dependency between iterations. There's no support for traceback. And due to these two loops, it kind of doesn't really scale to long reads, which can go up to millions in characters. Okay. So those are algorithm level limitations. So you could just look at the source code and kind of tell, okay, this probably doesn't work. Now there's also implementation level inefficiencies where you really want your hardware to do a good job at executing this. And basically observe that there's a limited parallelism in the algorithm as well, but that means this really affects hardware because you have to have your hardware go sequentially over all entries. And then you will have a limited memory bandwidth. So if you have this huge table and you frequently access all of these entries, then you have to spend most of your time just moving data instead of doing computation. And as we saw, actually, these bitwise operations, as I promised you, are cheap to compute in hardware, but that really doesn't do us any good if you're now just spending all of our time moving data and not spending any time on computation. Then what did we really gain? So we have 5 weaknesses of BiTAP, and in this prior work, we observed that GenASM, or we introduced GenASM. I guess I wasn't a co-author at that point, but my mentor Damla authored this paper, and she proposed GenASM, which basically massively improved this BiTAP algorithm. So they introduced this as an entire framework for multiple use cases, and they significantly improve on top of GenASM, on top of BiTAP to improve all of these weaknesses. So they make it much more parallel, such that it supports long reads. They introduce a algorithm to execute traceback, so they can report that cigar string that's really necessary. And then they really efficiently implement this as an algorithm hardware co-design. So they keep tuning algorithm parameters and hardware parameters and make sure both work together really nicely, and we get this nice end-to-end implementation of this. So it's not just someone who designs CPU and then some other person who has to use that CPU to program something. And it's also not just someone who designs an algorithm and someone else then has to go off and make that algorithm work somehow in hardware, but rather it's one team of experts who do both at the same time and can get ideal trade-offs from both. And as I will show, this leads to very efficient implementation. Okay, so this GenASM DC algorithm, so this is the forward calculation step. This is the part that's based on BiTAP. That's why it's the same table. Recall I showed this before. The first step that I took is simply realizing we can store all computed bit vectors from that code I showed earlier. And then somehow we can do traceback. So we first of all need to store all these bit vectors, which the earlier algorithm didn't do. It computed that table, but it only looked at the last column. So what the previous algorithm did is it looks at this last column to find the topmost zero, and wherever that topmost zero is, that's the edit distance. So here we find the topmost 0 in this row. It says 1 edit distance. And what they realized in this GenASM work is that, okay, if we store the entire table, we can do some traceback from here. This works by backtracking where the 0 came from, which turns out we have to follow some kind of path of zeros back to the top right. But it comes down to how did we arrive at that pink 0 over here that determined the edit distance. So those are the key innovations, and then there's some parallelism optimization, a greedy windowing heuristic that cuts down on both the O notation and it improves the compute parallelism, makes everything nice and regular. I'll refer to the paper for that though. John posted that in chat, by the way. Okay, so as I promised, this is a algorithm hardware code design. So they came up with both the software side of this new algorithm, but also they at the same time designed hardware for it. So this is now a bit of a electrical engineering exercise. How do you implement this algorithm hardware? And if you're from a computer science background, this will look more like a flow diagram to you than something that executes code, which kind of is what's happening. So you have a bunch of hardware that stays in place and the data moves through the hardware that does computation over it. So we have a host CPU and some main memory, and those send their data to the GenASM DC accelerator that builds these tables, and then a traceback accelerator that obtains the cigar string. So the GenASM DC accelerator consists of some on-chip memory, and it then does some computation over there, sends it to some more on-chip memory, these TB SRAMs, and from there the TB accelerator reads whatever it needs to do for achieving traceback. So I'll quickly animate through here, but as you can see, we start on the left essentially, and we give it query locations. We extract part of the reference and read strings from memory, send it to on-chip memory, do computation over there, write the table that we computed to more on-chip memory, read it again, do traceback, and we're done. So it's a nice flow diagram. What's interesting here is, and this the key benefit essentially of making this as a hardware algorithm co-design, is that we can match computation with bandwidth. So if you consider a CPU, for example, a CPU has a fixed amount of memory bandwidth for a given DRAM configuration, and it has a fixed amount of computation. You can't just dynamically add more compute units to your CPU if you like. So that means typically, unless you get very lucky in a CPU, you end up with either too much computational power that you cannot use, or too much memory bandwidth that you're not using. And either way, that's wasted resources, whatever you have. If you're just designing your hardware specifically for this purpose, you can perfectly match both and not waste anything. So this gives a much higher performance and power efficiency immediately. What's also interesting here is that we can quite cheaply scale this really well. So we can just put many of these hardware accelerators close next to each other on chip, as many as we like. And since they're quite small and area efficient, we can scale it up really far. So we can have, I don't know, if we desire to do that, we can have maybe hundreds of these compute cores on a single chip. Whereas, I mean, there are CPUs with hundreds of cores, but they get kind of large and bulky, and it becomes a big overhead. As I will show in the results, this is still very efficient, even if it's scaled up significantly. Okay, so let's look at some low-level details of this hardware accelerator. So it's designed with a technique called linear cyclic Stolic arrays. So essentially what you have here is a small processing core. This is essentially the bitwise operations that we need. So by the way, as you can see, so these are bit shifts and the bitwise OR and bitwise ANDs that I showed in the code earlier. So this is just a single instance of this, and all of these are 64-bit wires, I guess. But it's really efficient in hardware. In fact, these bit shift operations here, in hardware, they're not even operations. A single bit shift in hardware just means you move some wires over. So you could even ignore this part. And then it's just a 4-input AND gate, a 2-input OR gate. So it's at the lowest level of hardware, really efficient. And now we concatenate multiple of these compute processing cores into a systolic array. So we add to this combination logic some register to each end, and then we clone this over a bunch of time. So in each processing cycle, each of these processing cores does some work, and then it sends its data to the next guy. And it does some work, and it sends its data to the next guy. Does some work, sends data to the next guy. So we have these arrows going from one to the next. As you can see, these data arrows are pattern mask, which is a variable from the code I showed, and this old R vector, which is also from the code I showed. So it's essentially iterations. It's essentially iterating by sending the data across the systolic array, and it can just do so very efficiently because you're only sending you to your direct next neighbor, and they can be directly connected with wires. It's all very nice and efficient. And then, we loop back around, by the way. That's why it's a cyclic systolic array. So when this processing element is done, it sends its output over to the first one. The idea here is to be able to compute tables that are larger than the number of processing elements you may have. Okay, and then there's of course a bunch of SRAMs attached to these things for reading and writing. These are a bit boring, I guess. So for traceback, we again have some fairly simple logic. This is the other end of the same SRAMs that I just showed. And yeah, we basically read some data from each of these SRAMs. There's a mux over here that selects actually which data to exactly get from which SRAM part. And then it tries to reverse the operation of each of these bit vectors. So recall that match, insertion, deletion, substitution, these are each a different bit vector that was calculated in the code I showed earlier. And then we just need to do some simple bitwise logic to figure out, okay, which one was the one that generated the last 0 in our traceback step. Yes, and then, okay, we get the next arrow, we get the next pointer based on that, which goes back to the mux, and we repeat until we're done with traceback. So this looks quite efficient in hardware, hopefully. Now let's go into some evaluation methodology. So this was synthesized using a system Verilog. Maybe let me skip over this. So there's a bunch of hardware synthesis going on, basically a bunch of state-of-the-art software and hardware baselines at the time. And then it is evaluated on 3 use cases. I'll focus on the first one, this read alignment use case. So here we consider read mapping and the read alignment step in read mapping. So there's a Minimap2 and BWA mem that we use as the baselines in this case, and the GACT alignment accelerator in Darwin and the SILAX accelerator in GenASM. The other 2 use cases, by the way, are pre-alignment filtering and just edit distance calculation. But I'll not focus on these because I would consider them sub-problems of the first one. So the area and power can be, when synthesizing, we get a list of area and power numbers. So as you can see, we can have 4 main components here. This DC part is the forward calculation part, the logic part that generates the tables. This is essentially the systolic array. Then we have the traceback part, which is the logic for generating the cigar string. And then we have a bunch of SRAMs down here. So as you can see, the 2 major parts here are the TB SRAMs, which use 3/4 of all memory footprint, and then the logic for generating the table, which makes up about 1/8 of the logic area. And then in terms of power, the SRAMs are about 55% and about 30% from the logic area. But note that in total, this accelerator, which I believe this is already 32 copies of the accelerator here, this is just 10 millimeters squared. That's tiny, right? That's 0.1 centimeter squared, or about a hundredth of what a modern CPU uses. In terms of power, also 3 watts, that's like much less than your phone uses. 3 watts, it's like 5 volts at 0.8, 0.6 amps. It's nothing. You can easily supply that from a power bank, which is good because if you need this in a mobile genomics use case, let's say, you need this kind of low power consumption. Okay. So the so I'll focus on this first use case here, this realignment use case. So we are in particular observing there's speed ups across all baselines, such as we have 648x speed up on average over the software baselines in this case, and then there's 116x speed up over the minimap baseline. So the first one was what? BWMM. So BWMM is accelerated by 648x and minimap by 116x with the help of this alignment accelerator. Now this was for software baselines. Now we compare also to hardware baselines. We're developing a hardware accelerator, so it's just fair to not just compare to already fairly inefficient software versions. And you observe that on average, even over state-of-the-art software baselines, there's a significant speed up to be gained. And it's not just better throughput, but also better throughput per area that you invest. So if you consider a hardware accelerator, you don't really have a fixed area and power budget. Right? If your accelerator is too slow, you could always just make it 10 times larger. So that's why it's important to also compare throughput per unit area and unit of power. We can see that GenASM, even in this kind of really fair comparison, it does much better than Darwin. Then we have also a short read evaluation. So previous was long reads. And we observe again significant speed up over software baselines. And then I think I'm not going to be showing this, but we observe basically similar throughput and throughput per area and power numbers as before over hardware accelerators. So I mean, in summary, I guess, as in all of these papers, the results are good. Results are always good, and we can get significant speed ups with this algorithm hardware co-design over prior state-of-the-art in terms of both software and hardware. The full paper goes into much more detail in several areas, including computer science aspects like big O analysis, but also, of course, much more extensive evaluation and discussion of why exactly GenASM is better. And all of these additional use cases that I didn't go into now. So this is the paper. This was by the way presented in Micro 53 in 2020, and it's available online. It's also on arXiv, of course.